Hello friends, today we are going to talk about principal component analysis PCA. To start with, principal component analysis PCA is a linear dimensionality reduction technique with applications in exploratory data analysis, visualization and data pre-processing. The data is linearly transformed onto a new coordinate system such that the directions of principal components captured the largest variation in the data can be easily identified. Some mathematical deduction. So we start with the feature matrix AX, P by 1 having P columns x1, x2, xp. Now we have the variance of, we can calculate the variance of x from data as variance of x equal to sigma P by P. That's the variance covariance matrix of the feature matrix. Then we may consider the orthogonal transformation y equal to ux, where u transpose u equal to I. It's an orthogonal transformation. I is the identity matrix, and u sigma u transpose is a diagonal matrix D. That's possible. Then the columns of u are the eigenvectors of sigma, and diagonal entries of D are eigenvalues of sigma. So that's the eigenvector decomposition of the variance covariance matrix sigma. Now, if we arrange the diagonals of D as modulus of D11 greater than equal to modulus of D22 greater than equal to modulus of D33 etc. greater than equal to modulus of DPP, then Y equal to Y1, Y2, Yp are the principal components of X with variance of Yi equal to Dii. So, starting from the feature matrix X, we get a new mu matrix and orthogonally transformed matrix Y such that any two entries of Y's are uncorrelated, their covariance is 0, and variance of Yi are ordered from high to low. This we have found an orthogonal transformation Y of our feature matrix X such that covariance of Yi, Yj equal to 0 and variance of Yi are ordered from high to low. So that's principal component analysis. And where it is used, suppose we want to visualize the multi-dimensional data of the feature matrix X. So to draw a scatter plot, we can plot the y1, the principal component y1 in the x-axis and principal component y2 in the y-axis. That gives the most that gives the most observed scatter plot where we can see the variances in the data clearly. We could ignore the low variance components of Y helping in dimensionality reduction. So we have the dimensionality of P of the actual feature matrix. Now we can ignore the several low dimensional principal components of Y, and we can work with a lower dimensional data with effective results. So that's the use of principal component analysis. Explain variances. Suppose we have got 10 principal components, 1, 2, 3 up to n. Variance of first principal component is the highest, the second principal component is the next one, third principal component is the next one, and any two component is uncorrelated, their covariance is 0. A bit of history. PCA was invented in 1901 by Karl Pearson as an analog of principal axis theorem in mechanics. It was later independently developed and named by Harold Hotelling in 1930s. I'll stop here. The article is based on the Wikipedia page and principal component analysis. Like, comment, share, subscribe my video, and I am available for one-to-one sessions too. Thank you.